that was just explaining the framework and showing nice examples. The second lecture was about tricks, and the third lecture will be about some mathematics about the convergence and try to show some mathematical tools. So, just wait a minute for the technical problem. So, what we try to do in this lecture is to give some, not all details, but almost everything for rigorous proofs of convergence of the stochastic gradient in various cases, starting with the convex case and looking at non-convex cases. So, maybe I should start by reminding us about the mutations. So, as a cost function, as an expectation of the loss, you have examples, W with parameters. The stochastic gradient update consists in removing a learning rate times some update term that depends on a random example. And the first assumption I'm going to make, it's not going to be the last, is that the expectation of this update is the gradient of the cost. And I'm going to use h of W to denote the gradient, the patient of the cost. So first I'm going to discuss the convex case. And well, you only see what's going on. And make a convexity hypothesis. But I'm going to make something weaker than convexity hypothesis, but I call general convexity. And just this. It says that the dot product of the vector that goes from some weight vector to the optimum times the gradient is positive. And furthermore, that it doesn't go to zero except when we approach the solution. So I'll try to show the graph again. Let's see. So that's it. So if I take the vector going from WT to the optimum and compute the dot product with the gradient, I want this to be positive. I want to give this angle here to be active. Now I can discuss learning rates. There's something about the learning rates. To converge, I need to make smaller and smaller updates. So I want this term, gamma t times the update, to go to zero. There are two possibilities. Either I decrease the learning rates, or I decrease the updates. So let's have a look at this step. What can we do? So I can write the expectation of the square. It's going to be the expectation, the second moment of the gradient and the optimum, which is basically the variance of the update and the optimum, plus some second order expansion, different implication. So I can easily make a bound saying that this is smaller than A plus B times WT minus W star squared. So in general, this is non-zero. A is non-zero because if you remember when I'm at the optimum, when I draw examples randomly, there is still some noise and still flying, still hovering before the minimum. And this is a big difference in the batch case. In the batch case, this is not random, and A is usually zero. Except maybe in cases where you have non-differentiability. Like if you try to make a batch gradient in something like this, well, if you don't decrease epsilon, you just fly. That's actually a good example to keep in mind. If you decrease the epsilon, you bring it to go down. This is because in that case, the norm of the gradient doesn't vanish when you come close to the optimum. So in our case, I want to discuss convergence. I need to discuss decreasing convergence. And this is what I'm going to do in all this. So right now, in the convex case, well, maybe I should tell the story. At some point, someone initially gave a class in 81. Lecture somewhere. I don't know exactly where. I just found the lecture notes. I'm not sure I was wrong. And I saw the lecture notes, And I found that extremely clear. And since then, I've been copying the approach and going exactly with the same pace for my various products, because I think it's a great way to introduce the various tools towards the result. So for the convex case, I'm just going to do that and explain what's going on. So I'm going to present 3 proofs. The first one is very simple. It's to prove that the continuous gradient in continuous time converges because it is 0. Then for the batch case, but I'm going to take a batch case where A is non-zero, so something like this, where you have to mix, you have increasing rates. And then finally for the stochastic gradient. My point is to show that this proves that all the same. There are some proofs are changing in the way, there are some small differences, but it's the same field. So let's look at the continuous gradient. So we have WP, is a function, continuous of time, defined by the differential equation. And the first step, for A, is defining the Lyapunov function. Lyapunov means that when it's ht, so this function, which is the difference between the current W and the optimal, if this function goes to 0, I'm finished. The second step is to show that the Lyapunov function converges. So I write its derivative. And by my general convexity hypothesis, this is negative. So it's decreasing, it's bounded by 0. I was positive, so it converges somewhere. And the last step is to show that the gradient converges. If ht converges, means that its derivative goes to 0, means that this term here, which is the derivative, goes to 0, and I made before the hypothesis that this expression, dot product of W minus W star at the gradient, goes to 0 only when I come close to optimal. So I go to the optimal. So that's so far that's very easy. So let's discuss the batch gradient now. So the batch gradient, the update is like this. And I can define the same Lyapunov sequence this time, number of functions, this way. WP minus W star squared. And to prove it converges, I will be glad to say it decreases, it's bounded from below, so it converges. But that's not true exactly, because if you remember this graph here, it can go up a little bit sometimes. It's not strictly decreasing. So I need to do something more. So if I look at it at the sequence level, the idea is to look at the sequence as a succession of increments. Sometimes it goes up, sometimes it goes down. And I can separate my sequence in 2 terms. The sum of the time the increments when it goes up, and the sum of the increments when it goes down. So when it goes down, it's decreasing, it's bounded from below, you see. This one converges. But the one that goes up, I need to assume it doesn't go anywhere. So I define the sum of the positive increments of the sequence ut. So the plus here means that I just take the positive ones. And if I have a positive sequence, and if this sum converges, then everything converges. And in fact, yes, there is another way to see it. If the sum converges, this stuff cannot go to plus infinity. No way. Because the positive increments are not going to be able to carry it far away enough. And if it converges as well, I cannot have anything zigzag, because if I was zigzagging between 2 levels, I can do that. If I'm defining a line A here and a B, and was making zigzags, this sum would be there, diverge. So I'm going to use this. So I'm going to make some additional assumptions. First, I'm going to say that the sum of the gamete square converges, meaning that the learning rates decrease fast enough. And then this hypothesis that I described at the beginning, that the norm of the gradients is less than A plus B W minus W star. So I should point out that in the case of batch, you need A is 0, and everything is a lot simpler. But I take the cases here where A is not 0. And I want to show that these 2 additional assumptions are sufficient to show that HT converges. So I'll first start to assume that B is 0. So this is less than A. So I can write ht plus 1 minus ht plus just the positive increments. I expand it, and I get it smaller than this, and therefore smaller than this. And since A is a constant, given T square is convergent, this is convergent, and I would be enough. I prove that the sum of the positive increments converges, and therefore my sequence ht converges somewhere. In the case B, where B is different from 0, well, there is a trick. The trick, well, it's written in small here, and the details are exercised for the next time. So define a sequence unity that happens to be convergent to somewhere because gamma is convergent. And then we define the secondary ht, h', replace, everything simplifies, and the B goes away, and then things are the same. So I'm not going to discuss that too much, but if you run the mathematics, you'll see it just works. And the last part of step C is to show that the Patchwork converges. So this time I will have to do another assumption. I will have to say that sum of gamma t diverges. And the reason is that if my gamma decreases too fast, I'm not going to go anywhere. Suppose I'm here. I have a constant gradient. But if gamma converges, at some point I'm going to stop, because I can only go to a certain distance. And the way to prove this is to go back, if I come back to my previous slide here, in that expression, this one is negative. So to bound it, I just removed it. But this one is negative and can only help. I'm going to make this smaller. So I'm going to take this expression again and loop it. So I take it again without the plus. And I know that this is a convergent sum. And I know that H2 converges, so this is a convergent sum as well. So therefore, this has to be a convergent sum. And remember this WT and W star product product is positive. So if this converges, and if sum of gamma t diverges, it means that WT minus W star times the gradient goes to 0. And therefore, because of my general convexity hypothesis, this can only happen if WT goes to W star. And so I prove that Patchwork converges. It's a bit more difficult over here. Now we go to stochastic gradient. Yeah? The sum of gamma square converges. Sum of gamma diverges.
It's a very profound
you could change it a little bit if you change the hypothesis. You could change the gamma. This one, you need. It's absolutely necessary because suppose you have a constant gradient. If the sum of the gamma t converges, when you're going to flow the gradient, it's just going to stop. So this one, there is no way you can remove it. This one, the sum of gamma t squared, goes actually with this hypothesis. So in case when you would have a polynomial thing, you would change the square by something else. But in practice, it's not so important because this is pretty natural when you look at rotation. So you don't care too much about this. Now, the two conditions, sum of gamma t diverges, sum of gamma t squared converges. Typical example is 1 over t. But 1 over t to be very fast works as well. So you have a scope of allowable speed between 1 over square root of t, which doesn't work, to a little bit faster than 1 over t, so not that much. And so pretty much do that. So this time I take my stochastic update rule, where the update is no longer the gradient, but the random one. And I define a Lyapunov process. So the same thing. It looks like a sequence, but this is a random variable that depends on what sequence of examples you're going to find. And well, when you think Casino, you remember that the key idea was to somehow show that this HT is decreasing in value from 0. So think about the casino. You have values at each time you can lose or you can get. But mostly you lose a little bit more than you get. If you can gain, what you can gain is more or less limited. And we're going to add them, but each time it's a bit random. And it's not a big surprise that it's still going to work, it's still going to converge. So in fact, there is a trick. You remember what I said last time about this sequence. So I'm interested in bounding the series of positive variations. So I'm going to do exactly the same. But what is a positive variation when everything is random? So I'm going to define another variable, delta t. And I say it's going to be 1 if the expectation of ut plus 1 minus ut given the past. So the past is everything before. So at a given time, I know everything before, and I have an expectation of ut plus 1. If the expectation is positive, delta t is 1. So then y is 0. So when it's 0, you understand it's not a big problem. It means that at this step, my chances are to lose. HT is going to decrease, and we're going to be bounded by 0. Everything will be fine. When it's 1, I want to be sure that it's not going to be too bad. So I'm going to define my sum of positive increments, as being the sum of the expectation of delta t times this increase. So this plays about the same role as the plus sign that I had in the other case. And well, if you look in the book, maybe I don't really have time to explain why this is so more than I can. But if you look in the book like this one, you find a theorem, the proposition, nudge a little bit, and you get that if this sequence is convergent, then ut converges almost surely. So that's a good tool. It's the tool we're going to use again and again and again. Also, you can see that if you have this condition, if this sequence is convergent, you can see by a little bit of manipulation that E of so well, maybe I should you can see that the expectation of ut is bounded. And that's quite easy. You write it as a sum of expectation of ut plus 1 minus ut between pi between 1 and t. I'm just going to write it as plus the expectation of source. So this one we know converges, and this one is negative. So therefore, expectation of ut is going to be bounded. It's going to be useful later. That's why I'm saying this. So let's go with the step B. Where is my step? So I'm going to make the same assumptions. Sum of gamma t squared converges, and these boundedness assumptions and the gradients. And I'm also going to take the assume b equals 0, and the case being different than 0 can be dealt with the trick. So I write it, expectation of ht plus 1 minus ht given the past is this. I just expand, and I have the expectation of my update, which is the cost, equivalent to the cost. And this term is negative, I can remove it, and I get just gamma t squared a. So if I have a delta t inside, it's not going to change anything. So now I've shown that my series of positive increments is convergent. Therefore, I've shown that ht converges somewhere. And now the step C, same assumption, sum of gamma t diverges. And the same technique. I'm going to go back, look at this line here, because in this line I made a very force boundary by removing something that was important. I'm going to take its expectation. If I take the expectation of this, I'm going to find this expectation here and this thing here. And you recognize A here. So I told you later, expectation of UP is finite. So this is a convergent sum. The sum of these terms is convergent. This is a convergent sum. So this has to be. Since sum of gamma t diverges, that means that the expectation of this product here goes to 0. If the expectation goes to 0, the expectation of something positive goes to 0, it means that this thing cannot remain non-zero on a non-negligible set, and probability or set of probability more than 0. So therefore, the limit, well, therefore, this stuff goes to 0, almost surely, and therefore the W star, W goes to W star, because of the general convexity hypothesis. So the message here I would like to show is that these three proofs, the continuous time, the discrete batch gradient, or the stochastic gradient, they're all the same. They're essentially the same. The only differences are the tools you use and a few little technical details. The tools are more sophisticated, they afford more flexibility, but they still follow the same framework. So now we've proven, under rather reasonable assumption, that we converge in the convex. But this is still far from the general case. We instead with cost functions that are non-convex, case where we have several local minima, sometimes quite often actually several global minima, where the cost function is split in various symmetrical areas, and between you have critical subspace where everything goes bad, but then you get saddle points. It's a massive landscape. So the first thing to do is to look at how they did it for batch. Because lots of people study Drag's algorithm, including the non-convex case. And if you look, that was actually before I was born. In the Russian literature, there are some nice ideas of local confinement. So you partition your space into attraction basins. Then you make sure you find the conditions under which probability remains in each attraction basin, which in batch gradient is quite possible. In each basin, you define the Lyapunov function and you describe everything that's going on. So for batch, that works. For stochastic gradient, it works very poorly because even if you're on a local minimum, you have a chance to go out of the basin before to another one. So if you want to use that kind of result, you have to say, to make strange things, strange hypotheses like I'm going to be confined to the attraction basin, or with probability 1 minus delta, where delta is the probability to get out. And it's not very attractive. And in fact,
why isn't it possible to confine in the batch case?
No, the batch case is possible to confine.
Okay, but when you say confine, it's strong constraint on the region that's...
Yeah, say starting at some time t0. Starting at some time t0, you remain in a fraction basin foil. That's confinement.
If you prevent batch gradient to do that by just...
You prevent the batch gradient to do that because at some point you're low enough in the basin and your logging rate has become small enough that you cannot get out.
Can you explain with me, how do you confine? What is the device to confine the territory of
in the case of batch?
Yeah.
Well, so you're making little steps like this. Up or down, depending on the gradient. So, and this is an attraction value. So of course, as soon as you enter it deep enough, the gradient times the logging rate is no longer enough to make you drop. So if you update is to subtract to each WT the gradient times the logging rate, you're going to stay in that domain. But
So when you say I confine it, you mean I prove that it cannot escape
yeah.
the basin, but it's not like you have a special thing in the algorithm.
Oh no. The confinement in my code means proving that it cannot escape. But in the case of stochastic, there is always this stochastic noise. You know, even if you're here, there is a chance that at some point you get a sequence of row of examples that just get pulled up and do the next one. So you cannot confine. You cannot obtain a theoretical guarantee that you're going to stay in the same attention class. And of course, you could do quasi-confinement. A lot of things that are quite mean. Very attractive. So I'm going to start with the standard assumptions. I'm going to say that there is a cost, it's positive. I'm going to assume it has continuous second derivatives. But the loss function, if you remember, has to allow derivatives in differentiable everywhere except maybe on the zero measure set. I'm going to make there is a square next to here. So make the assumption for the learning rates and the assumption on the size of the derivatives, saying that they don't grow too much with the volume. And one of the things that need is I still need a confinement result because one of the problems we have is we could go to infinite forms and just get lost. So what I'm going to assume here is something that's usually reasonable. I'm going to assume that my cost function is something with plenty of local minima, but when I look at it on a large scale, it's somehow convex. So that means, if you take something like k-means, for instance, well, if you take all the centrally far away from the points, from the data points, it's clear that you will get globally convex, or a certain scale it's convex. If you take a backward network, it's not so clear because of the signal if they're flat. But if you add to the cost function weighted k terms plus gamma WT squared, then you again have this property. It's a very common property in learning systems that they have some, if you look them from far away, they're globally convex. So here is what I'm going to assume. So this is the zero. And I'm going to assume there is a circle at size B. If I'm outside of this circle, then the W times gradient is greater than 0. I'm going to say that if I'm outside this circle of size B, the gradient takes me towards origin somehow. Good enough. And the second assumption is something that's quite weak, actually. So it's quite mild. So that there is a circle that's bigger than B. And within that circle, the updates are bounded. So if the updates were not random, that would be quite reasonable. You know, if they're continuous, that's good enough because they're compact. Because they're random, it's a little bit stronger. It's not that strong because if you look at actual functions, if the examples themselves are bounded, in general, it's sufficient. And when I do this, I get this nice result. So what does this mean? It means that if I whatever the row of examples is, with probability 1, if I wait long enough, my WT is going to be confined in a big circle that's a little bit bigger than E, for instance, with probability 1. So how to prove this? Well, I define the Lyapunov process, HT equal maximum of E and WT squared. And I do A, B, C. I'm not going to do it again now. I do it 3 times I will do it. So it's exactly the same stuff. When you do this, you conclude that basically HT goes to E. And therefore, that you can safely say that after some time, WT will be within a circle of size 2, or radius 2, square root of 2. So the good news is that we're not working in a compact set. We can assume now that WP is less than E. We know that before EP1, after long enough, it's going to be 2E. Okay, yes. And because a lot of things are continuous when I'm going to make all the derivations, well, all continuous quantities will be bounded. And that's going to make everything look a little easier. I'm not going to have to deal with this little trick with D0, D0, everything is bounded. And now, with the same hypothesis, so all the standard ones plus these two, I can show that C of WP converges somewhere. Not necessarily 0, not necessarily optimal. And that the gradient of C converges almost surely to 0. Which means I'm going to go to some interesting points. How to prove this? Well, define the Lyapunov process. This time we take the function itself. Step B, so it converges. Step C is more difficult. I have to define a secondary Lyapunov process, which is going to be GT, which is going to be this gradient here. And do ABC again to show that this is just 0. If we look what this means I'm going to extremal points. So this one, this plateau, is something that ruled out because of this global confinement. If I don't have the global confinement, I can still prove something similar, but I can go there and be lost in infinity. That can happen. Things like local maxima here. But remember, I have a built-in noise in my process. It's not clear that this noise is isotropic. I can easily construct examples where a stochastic gradient process is going to be stuck on something like this. Example where the noise is very strange, not going to move you around. But in a realistic case, this is unstable. But you can get stuck for a long time. Right? It's also fully flat. Yeah. And local minima, well, that's it. So basically, we can say that we can go to some of these points, but these ones are rather unlikely and likely, and these ones are ruled out by the local time. You have to reason about that process. You notice that I didn't say anything about the speed right now. To discuss the speed, there are two things to discuss. First is what's happening at the end. You know, when I'm at the end of the convergence, I'm in a local pattern, and have a good chance to stay here. Not certain, but I have a good chance to stay here, and I can estimate WT minus W squared, W star squared, and we can try to make some derivations. And there is also the speed during the search phase, you know, when I try to find the good pattern and so on. And in terms of speed time, this appears as a constant. This is the asymptotics, but in practice, the constant is what matters. And for discussing this, I must say it's still a very open problem, we say. But still, even when you do this, you try to analyze the finite convergence speed. If you remember that there is a slight difference between learning and optimizing, you get something bigger that's called optimal learning algorithms through the sequence. And that's going to be the next lecture.